In this video, we will be calculating the shear capacity using ACI simplified method, the ACI 318 detailed method, and the AASHTO LRFD general procedure for the section shown. This is a rectangular section with both tension and compression steel and no transverse reinforcement. We can see that it's a simply supported beam with a length of 216 inches or 18 feet and a distributed load W. And this was a beam that was tested at the University of Texas. And the failure load measured during the testing was 13.3 kips per foot. So we'll use that to calculate our shear and our moment at failure. We can see that our concrete compression strength is 4 KSI, which was measured. Our modulus of elasticity was 3,840 KSI, which was measured. And then our Fy is 69 KSI, and we have 5 number 11 bars in the bottom and the top. Our D is just equal to our total height minus our cover minus half the diameter of one of our number 11 bars, which would give us a D equal to 21.3 feet. We'll also need some other parameters for our shear estimation in using the AASHTO method. We'll need our maximum aggregate size, which is 1 inch. And we'll also need the distance between different crack control reinforcement. Here we only have our top and bottom steel is our only crack control reinforcement. So we have our D minus our top cover minus half of our bar diameter to get us the distance between these two layers, which will give us a distance of 17.6 inches. If we had other layers of steel in between, so in a beam where you have other layers of steel going up and down your cross section, that distance is just between those layers of crack control reinforcement in the side. The first thing that we need to do is we need to find our shear and moment diagrams for our simply supported beam with the distributed load. And we need to do this so that we can find the shear and moment at our critical section. For both AASHTO and ACI for non-pre-stressed member, the critical section is going to be a distance D away from the face of the support. Here we don't have any support information, so we're just going to assume that the face of the support is the end, or is the center line of our support. So a distance D away from the face of the support will give us our critical and or critical shear and critical moment. We can find our maximum shear, which would be 120 kips, and our critical shear here. We are have a linear slope equal to our distributed load, so we can find our shear at critical equal to 96.4. We can also find our max moment and our moment at the critical section. So our max moment at midspan and our moment at the critical section of 2300 kips. In both ACI and AASHTO procedures, when we're looking or when we're using our shear demand, we're going to use the shear demand at the section where we're calculating our shear strength. So we're going to find our shear strength at our critical section. So we're going to use the critical shear and critical moments in our shear strength expressions. The other thing we can do is we can calculate our shear span to depth ratio. So the shear span for a distributed load is just the ratio of our maximum moment to our maximum shear. So you can see here our max moment we found to be 6,464 kip inches, and our maximum shear was 120 kips. So our shear span is just 54 inches. Our shear span to depth ratio is 54 divided by 21.3, which will give us 2.54. We can see that this is greater than 2, so we can use our normal sectional shear approaches. If we had a shear span to depth ratio less than 2, then we need to consider this as a deep beam member, and we can use the strut and tie method in that case. We're now ready to calculate our shear capacity using our different methods, and we'll start with the simplest. So using the ACI simplified shear procedure, we'll get our VC is equal to 2 times lambda, which is 1.0 because we're using normal weight concrete, times the square root of 4,000 psi, times our BW, which is in this case 36 inches, and our D is 21.3 inches. And I'm going to take this times 1 kip per 1,000 pounds to convert our units to kips, and we'll get 97.0 kips. We can then see we don't have any transverse steel, so our VS is going to be equal to 0. So our AV is equal to 0. So we have no transverse steel, so we have no VS component. Then our total shear resistance, our VN, is just equal to our 97.0 plus 0 equals 97.0 kips for our simplified shear method. We'll next use our detailed shear method. And to use the detailed shear method, we're going to calculate a couple parameters first. We'll calculate rho W, and we'll calculate the ratio V sub U times D sub P divided by M sub U. So first, our reinforcement ratio considering the web width. So we have our total area of steel, our tension steel, which is 5 number 11 bars, 1.56 square inches, divided by 36 inches times 21.3. Will give us a rho W here of 0.0102. And then our ratio here, considering the shear and moment at the section, at our critical section. So our V sub U is 96.4 kips. Our D is 21.3, and our M sub U is 2,300 kip inches. So we'll get this ratio to be equal to 0.893. So then we can plug all these values into our expressions found in section 22.551. So we'll get our VC equal to the minimum of these three equations. So we'll calculate the value from each of these three equations. So the first equation here, we have 1.9 times 1.0 times the square root of 4,000 psi plus 2,500 times 0.0102 times 0.893 are two values that we found. And then all this times 36 inches times 21.3 inches will give us a value of 109.6 kips. So dividing by 1,000 pounds per kip to get that into kips there. Our second equation here will give us 1.9 times 1.0 for normal weight concrete times 4,000 plus 2,500 times 0.0102 times 36 inches times D, 21.3 inches, will give us a value here of 111.7 kips. So again, dividing by 1,000 pounds per kip. And then our last equation here, we have 3.5 times 1.0 for normal weight concrete times square root of 4,000 times BW, 36 inches, times 21.3, our D, will give us a value here of 169.7 kips. So we're taking the minimum of these, so we can see that our minimum here is 109.6, so that's our minimum value that we'll use. Again, we have no shear stirrups, so our VS is still equal to 0, and then our VN is just equal to our VC, which is equal to 169.7 kips. And that's how we use our detailed shear method. We're next going to use the AASHTO LRFD general procedure. So normally when we're doing a shear design, we'll first do the flexural design. So that means that we'll have our flexural strength already. So AASHTO uses the flexural strength in the determination of what's called an effective shear depth. So our effective shear depth is D sub V, and it's equal to our nominal moment capacity M sub N divided by ASFY plus APS FPS. So non-pre-stressed steel plus pre-stressed steel component. We don't have any pre-stressed steel component, so all we have is our non-pre-stressed steel. So we have 5 number 11 bars with a yield strength of 69 KSI. Our MN, we'll say that we found before for this section, is equal to 10,274 kip inches. So we can find our DV equal to 19.1 inches. AASHTO also tells us that this DV doesn't need to be less than the greater of 0.9 D sub E and 0.72 H. So for us, 0.9 D sub E is 19.2 inches, and 0.72 H is 17.3 inches. So the max of these is 19.2, so that means that our D sub V doesn't need to be less than that value. So we'll use a D sub V equal to 19.2 moving forward. Next, we need to find our crack spacing parameter, which is S sub XE. We need to find this because we do not have minimum transverse steel. If we had minimum transverse steel, then we wouldn't need to find this parameter. So we can plug in our values that we found on the first slide, and we'll find that our SX here is equal to 17.6 times 1.38 divided by 1 inch plus 0.63, which will give us an S sub XE equal to 14.9 inches. The next thing that we need to do is we need to find our tensile strain. So this is the strain in the concrete at the location of the centroid of the tensile reinforcement, so epsilon S. And we use this value to tell us how effective the concrete's going to be at resisting shear, and also the crack angle theta. So for us, our epsilon S is going to be equal to the absolute value of 2,300 kip inches. So this is our moment at the location that we're interested in, that where we're calculating our shear, our critical section, and divided by our DV, which is 19.2 inches. we don't have any N sub U component for this problem, or yeah, we don't have any pre-stress component either, and we also don't have any pre-stressing force. So we just need to add in here the absolute value of 96.4 kips. We divide this by our denominator, which we again don't have any pre-stressing component, so we only have our 29,000 KSI times our 5 number 11 bars. And we'll find our epsilon s is going to be equal to 0.000956. Note that it's positive, so we have a tensile strain here. If it was negative, we would have a compression strain, and we would also need to include the stiffness or restraint provided by the concrete. So just if your epsilon s that you find here is less than 0, then you need to change your denominator to include the concrete stiffness. So E sub C times A sub CT. But for us, it's greater than 0, so we're okay here. All right, the next thing that we can do is we can find our concrete effectiveness factor. So for us, we don't have our minimum transverse steel, so we have this second component that we need to include. So we'll have 4.8 divided by 1 plus 750 times epsilon s 0.000956. Times 51 divided by 39 plus our S sub XE, which we found to be 14.9. And we'll get our beta here to be equal to 2.65. And we're going to use this beta on the following slide to find our concrete shear component. We can also use our strain at the level of our tension steel to find the angle of our compression or the crack angle. So this will be 29 plus 3,500 times our strain that we found on the previous slide, 0.000956. So we'll find our angle here to be 32.3 degrees. And we would use this angle if we had a steel component. So if we had some steel, we would use this angle to help us determine how much steel is crossing our cracks. So how much steel contributes to our shear strength. Since we don't need to use it. But we can use our beta to find our V sub C. So our V sub C here is going to be 0.0316 times our beta, which we found on the previous slide, 2.65, times the square root of F prime C. In AASHTO, all of our units are KSI. So just make sure that when you're using AASHTO under the square root, we use KSI. Where in ACI, we're using PSI. So just note that difference because that'll give you much different answers. So then times our 36 inches and then times 19.2 inches, our shear depth. And this will give us a V sub C equal to 115.8 kips. We don't have any steel, and we don't have any vertical pre-stressing component. So our V sub n is just equal to our V sub c, which is 115.8 kips. So this is our V sub n value using AASHTO. We can then compare our actual shear capacity with our estimated shear capacity. We saw that our section failed with a shear of about 120 kips, and our estimated shear capacity for using our simplified procedure was about 97 kips. Using the detailed ACI method, it was about 109.6 kips. And using the AASHTO general method, we had a value of 115.8 kips. So you can see that our AASHTO procedure in this case was our most accurate estimation. And in this case, all of the estimation methods were conservative compared to our experimental results. So that concludes this example problem.